two particles created together get separated by billions of miles. You measure one, and instantly the other one responds. Not after a delay, not after a signal travels across space. Instantly. Einstein called it spooky action at a distance because it broke everything he believed about how reality worked. He spent the rest of his life trying to explain it away, but he could not. Nobody could. Because quantum entanglement is real. It has been tested, confirmed, and demonstrated in labs all over the world over many decades, and it does something that should be physically impossible. Connects two objects across any distance with zero time delay. And here is what simulation theory says about that. There is no mystery here at all. In a simulation, two entangled particles are not sending signals to each other across space. They are two values in the same piece of code. When the program reads one value, it updates the other at the same time because they are the same variable stored in the same memory location. Distance between them in the simulation means nothing because the connection is not physical. It is computational. This is not a loose metaphor. This is a technically precise description of how shared variables work in any networked system. When you understand that, quantum entanglement stops being one of the most confusing phenomena in physics and becomes one of the clearest pieces of evidence we have that this universe is running on code. If you're ready to uncover the truth behind our simulated universe, hit like and subscribe to join us on a journey through the mysteries of simulation theory. Let's get started. Let's start with the basics of simulation theory and why it matters for understanding quantum entanglement. Simulation theory says our universe is not physical in the traditional sense. It is a constructed program running on some kind of computational infrastructure far beyond what we can currently access or understand. Think of it like the most advanced software system ever built, and we are processes running inside it. Now, in any software system, there are things called shared variables or synchronized data. These are values that are linked across the entire system. When one is updated, the other updates immediately, regardless of where in the system they are located. The distance between two processes in a network means nothing for a shared variable because the connection is not physical, it is logical. It exists at the level of the code itself, not at the level of the physical environment the code is running in. Quantum entanglement in physics is the discovery that two particles can be linked in exactly this way. Measure the property of one particle and the partner particle instantly takes on a complementary property. No matter how far apart they are, no matter that nothing physical could have traveled between them in that time, the update happens instantaneously. This has been confirmed in experiments stretching the distance between entangled particles to hundreds of kilometers and beyond. The results are always the same. Instant correlation. Now, the standard physics explanation for this is vague and ultimately unsatisfying. It essentially says the particles share a quantum state, and measuring one collapses the state of both simultaneously. It does not explain the actual mechanism. It does not explain how that correlation happens across any distance with zero time delay. Simulation theory provides a clean and complete explanation for that mechanism. And that is exactly what we are going to walk through in full detail today, starting with why the standard explanations continue to fall short. Here is why quantum entanglement is such a problem for traditional physics. In standard physics, nothing can travel faster than light. That is one of the most tested and confirmed rules we have. Every signal, every force, every piece of information is limited by the speed of light. It takes light about 8 minutes to travel from the sun to Earth. So any signal sent from the sun would take at least 8 minutes to reach us. Quantum entanglement violates this completely. When two entangled particles are separated and one is measured, the other responds, not in minutes, not in seconds, not in any measurable time at all. The response is instantaneous. This means whatever is connecting these particles is not a signal traveling through space. It bypasses space entirely. Physicists have tested this at greater and greater distances to rule out any possible hidden signal traveling between the particles. They have run experiments across entire cities, across hundreds of kilometers. The results are always identical. Instant correlation, and the speed required to explain it as a traveling signal would have to be many thousands of times faster than light, essentially infinite speed. Now, in traditional physics, that is simply not allowed. It breaks the foundational rules of the model, so physicists have been forced into uncomfortable positions. Some proposed hidden variable theories, saying the particles were always correlated before separation. But Bell's theorem and subsequent experiments effectively ruled those out. Some say information is not actually being transmitted, so technically no rule is being broken. But that explanation just renames the problem without actually solving it. Simulation theory does not face this problem at all, because in a simulation, the physical distance between two particles is simply not the relevant factor. The relevant factor is how their data is stored and linked within the code, and that is what we are going to break down next. Picture this. You are a developer and you have just built a networked game. Millions of players are inside the same virtual world at the same time. In this world, two objects are linked. They are designed to always have opposite values. If one is red, the other is blue. If one goes up, the other goes down. Now, a player in Tokyo interacts with one object. A player in New York has the other object. At the exact same moment the Tokyo object turns red, the New York object turns blue. There was no signal sent between Tokyo and New York. There was no data packet flying across the ocean. There was just a rule in the code that said these two values are linked. When one updates, the other updates at the same time. That is how entanglement works in a simulation. The two particles are not sending signals to each other. They are two display outputs of the same underlying variable in the program. Measuring one in the simulation reads and locks the shared variable, instantly updating both outputs at the same moment, because the program does not need to send a signal across the simulated space. It just reads and updates the shared data structure directly. Now think about what that means for how we understand space itself. In a simulation, space is rendered. It is a visual representation of position within the program, but the underlying data does not need to respect the spatial distance it is rendering. Space in the simulation is just a display system. Code underneath operates at a completely different level, without any of the spatial limitations the display layer imposes on the players inside it. And quantum entanglement is precisely the place where the underlying code layer breaks through the display layer and becomes briefly visible to the people inside the simulation. This is why it confused Einstein so profoundly. He was trying to explain a code-level phenomenon using display-level physics. And those are two completely different systems that do not operate by the same rules. Here is the part that makes the simulation explanation for entanglement so much stronger than any alternative. 2022, the Nobel Prize in Physics was awarded to three scientists, Alain Aspect, John Clauser, and Anton Zeilinger, for their experiments confirming quantum entanglement. Their work definitively proved that entanglement is real, that the correlations cannot be explained by any pre-existing hidden variables, and that the connection between entangled particles operates without any local physical mechanism. This was not a minor scientific result. This is the physics community officially recognizing that reality at its deepest level does not behave like a physical system. It behaves like a networked data system. Now, here's the key technical point. In computing, there is something called a shared memory architecture. This is a system where multiple processors can read and write to the same memory location simultaneously. There is no delay between them because they are not communicating through a network. They are both accessing the same piece of data directly. Quantum entanglement matches this model exactly. Two particles sharing an entangled state are two processes with read and write access to the same memory location in the simulation. When one is measured, it writes a value to that location, and the other reads it at the same time. Zero delay because there is no distance to cross at the code level. Simulated space between them is just the display layer. Additionally, physicists have now demonstrated entanglement not just between particles, but between larger objects, including tiny diamonds at room temperature. This scaling matches exactly what you would expect from a simulation where entanglement is a property of how certain data structures are defined, rather than a quirk limited to subatomic particles. So here is what we actually know. Quantum entanglement is real. Instantaneous correlation across any distance is real. The standard physics explanations leave the underlying mechanism completely unexplained. The simulation framework provides a clean, complete, technical explanation that matches the observed behavior precisely. Two entangled particles are two outputs of the same shared variable in the simulation code. Measuring one reads and locks that variable, updating both outputs instantly because the connection exists at the code level, not at the spatial display level. Speed of light limitation applies to signals traveling through the simulated space. It does not apply to data operations happening at the level of the underlying code. That single distinction resolves the entire mystery. Think about how that shifts your understanding of the universe. Thing physicists called the deepest and most disturbing mystery in all of science turns out to be completely understandable once you know what kind of system you are operating inside. And if entanglement is a standard feature of a network simulation, it means the simulation has a communication layer underneath physical space that we can detect and measure, even though we cannot yet fully access it. We are observing the infrastructure of the program. This is not abstract philosophy. This is a specific and testable framework with experimental support at the highest level of physics. Pay attention to quantum research, because every advance in understanding entanglement is also an advance in mapping the underlying architecture of the simulation you are living in right now. Now we want to hear from you. Does the network synchronization explanation for quantum entanglement make more sense to you than the standard physics version? Or do you think there is a better explanation? Drop your thoughts in the comments below. We read through everything, and this is one of the most technically grounded arguments for simulation theory we have ever covered on this channel. If you enjoyed this exploration of simulation theory, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an upload. And if you're ready for more interesting content on the simulation theory, make sure to check out our other videos. Thank you for watching.